All right. So what I want to do tonight is finish up on chapter five, the building blocks of radios, and then move on to chapter six, digital modes. Now, excuse me, I saw and heard some eyes glazing over last week, so I'm going to go very quickly through a brief review of some basics and uh, maybe the material last week and this week will make more sense once I go through this. And my apologies if this takes you back to your technician class days or if you're already very familiar, but let's see what we can do here. Yeah, here we go. Well, Um, this is getting right to the edge of engineering, but I promise uh, I will be very brief here, and this is the worst math you're going to see tonight. There, the theory says that any radio signal can be thought of as a combination of sine waves, and the equation there is the amplitude times the sine of 2 pi times the frequency times time. So, or you can also define it as a cosine. And a sine wave is a pure tone. If you want to think of a sine wave, if you have a hearing test, those tones you hear, which don't have very much character at all, are sine waves because they contain only one frequency. So, and your voice is made up of the voice is made up of sine waves on different frequencies and different amplitudes. Um, musical instruments play uh, musical instruments when they play the same note are actually emitting different combinations of sine waves on different frequencies. So with that in mind, so you can see a sine wave is just the sine function that repeats in time. And the amplitude is how strong it is, or in other words, the peak of peak value of the radio signal or the sound or what have you, or the voltage above the zero, above zero. And it's the same amplitude above and below that zero line. And then the period is the amount of time it takes for the sine wave to repeat, or in other words, go through all 360 degrees of the function. And then the frequency, if the period is the time it takes for one waveform to complete in seconds, then the frequency is the inverse of that, or in cycles per second, or hertz. So uh, your speaking range is in hertz to kilohertz. Radio signals generally go from kilohertz to megahertz to even gigahertz. In other words, they span a wide range. Uh, Very briefly, amplitude and frequency modulation, I'll illustrate here. If you have a carrier, amplitude modulation varies the strength of the carrier. And you can see in this red trace in the middle, the carrier, which are sine waves at a higher frequency, and the strength is modulated by this low frequency modulating signal. For FM, at the purple trace at the bottom of the screen, you can see that the frequency of the carrier changes depending on um, dependent on the amplitude of the modulating signal. In other words, for high positive voltage, the frequency might be higher, and for a high negative voltage, the frequency might be lower. And phase modulation looks very much like frequency modulation. The difference is in amplitude modulation, the frequency of the carrier is constant and the amplitude changes. In frequency modulation, the amplitude is constant and the frequency changes. Um, Another way to look at it is in both the time domain, which is what you'd see on an oscilloscope trace, and in the frequency domain, in other words, the frequency spectrum. So the carrier on the left is a single frequency tone, so you can see it's just one line on the spectrum. An AM signal, an AM signal would show the carrier in green here and two sidebands. Um, and if the audio signal is just a single tone, the two sidebands would just be single frequency lines above and below the carrier in frequency. And then, excuse me, and then if we're modulating the carrier with just a tone, a single sideband signal, in this case, the upper sideband would be a constant level at a single frequency above the frequency of the carrier that's no longer there. Now, in real life, sorry, in real life, the modulating signal is going to, or here called the baseband signal in the upper left, is going to be a number of different tones and a number of different tones, in fact, changing. So you can hear the pitch of my voice changing and perhaps the intonation also, which the intonation will emphasize different frequencies that are present in my voice. So amplitude modulation below that shows that the spectrum, the spectrum of the modulating signal shows up both above and below the carrier frequency. And then on the right-hand side here, you can see that upper sideband modulation, the frequency, I'm sorry, the baseband spectrum shows up in RF above the carrier frequency, or for lower sideband below the carrier frequency. So I hope this makes a little bit more sense. And now let's get into the mechanism of how modulators work a little bit. Oh, sorry. Oh, yeah, sorry. Let's do harmonics. Uh, the fundamental frequency of a sine wave is just that sine of 2 pi times frequency times time. Second harmonic it goes at twice the frequency. Third harmonic at 3 times the frequency. Fourth harmonic at 4 times the frequency, and so forth. Another name for the fundamental frequency is the first harmonic. Now, the FCC doesn't like radio hams to transmit harmonics either of the carrier frequency or of the modulating frequency, because one of the things you might remember from last week is the FCC wants you to transmit at the minimum bandwidth necessary to get the information across. So, um, so the idea is that your modulation is clean. In other words, it doesn't introduce harmonics of your voice frequencies, and the transmitter is clean. In other words, it doesn't introduce harmonics of the radio frequencies. Now, there's a concept called linearity. And a circuit is linear if its output reproduces its input exactly, except for amplitude. So the relative frequencies of the components of the input signal are the same on the output, and the relative strengths of the signals on the input are the same on the output. Now, a circuit is nonlinear if its output includes harmonic and mixing components that are not present in the input. The unwanted outputs of a nonlinear circuit are called distortion. Now, that's why we talk about, that's what we mean when we talk about distortion. Now, no circuit with tubes or transistors or integrated circuits uh, is going to be perfectly linear, but uh, you can make circuits that have a very good approximation to perfect linearity. In other words, the distortion products are very small compared to the desired output. Now, keep that in mind because, okay, we'll talk a little bit about distortion. Harmonic distortion is caused by nonlinear circuits generating harmonics. Um, in other words, multiplying the input frequencies by 2, 3, 4 times, etc. Typically, human beings, your ears, if you're listening to high fidelity audio, you can hear harmonic distortion as small as 0.1%. And that's not just audiophiles talking, that's normal people. On the other hand, in the communications radio, you can understand voices through a speaker, for instance, that have 5% or perhaps even 10% total harmonic distortion. And now, the sound may be tinny or muffled or a little bit hard to understand. And there's an old joke about announcements when you're riding the subway, not being able to understand. That's because of distortion. There's another kind of distortion called intermodulation distortion caused by harmonics of different signals mixing to create new frequency components. Now, typically, the intermodulation distortion of amateur transmitters and amplifiers is around minus 30 dB, or about about that 1/10 of 1% in power that you can hear at audio. The FCC likes the intermodulation distortion to be as low as possible because IMD means that components of the signal occupy a broader spectrum. So now with that in mind, let's talk about mixers. Uh, Mixers and modulators use a math trick. And that is if you multiply, remember I said that you could represent uh, pure signals as cosines, cosines of frequency times time. Well, I'm gonna simplify that a little bit. I'm not gonna put the whole long equation in there. But if you multiply two cosines together, you get two products. One is the cosine of the two frequencies added together, and the other is the cosine of the difference of two frequencies. And if you're just doing a math identity, half of the size of each of those two components is half of the input of the strength on the left-hand side of the equation there. So if alpha is the carrier frequency and beta is the modulating frequency, then the result, which has no component at frequency right at frequency alpha, is double sideband, or the output of a balanced mixer. Now, AM modulators don't work quite the same, so they don't eliminate components on the carrier frequency. And so that's modulators, but mixers work the same way. The two frequencies that output are the output of a mixer are the sum and difference of the desired frequency and the local oscillator, or the difference, the sum or difference of the image frequency and the local oscillator. local oscillator. The output of a mixer, which can be higher or lower, although we normally think of it as being lower in frequency, is the intermediate frequency in a receiver. But you got to keep in mind that mixers work the same for both the uh, frequency range that you want to convert to the intermediate frequency and the image frequency range. So if for instance the desired frequency range is above the uh, local oscillator frequency, then the intermediate frequency will have the desired frequencies mixed down uh, from that high side difference down to the intermediate frequency, but it works the same for the image. If the image frequency, which is lower than the local oscillator, will also get mixed down to the intermediate frequency. That's why we put filters. That's why we put filters uh, on the radio frequency input to a mixer, and receivers are designed so that uh, the image frequency range is filtered out. So let's see, what do we got here? Okay. So I also want to talk about phase for a minute. I think we sort of skipped over that. And I want to talk about three different phases. The phase is the difference between two signs on the same frequency, but not necessarily occurring at the same time. So two signals are said to be in phase if uh, their zero crossings or their peaks occur at the same time or at the same angle of the sine or cosine function that represents them. So in the top trace here, wave one in blue and wave two, the dashed line that's inside the blue trace, are in phase, and so the sum of them is just the sum of the amplitudes at each point along the trace. If two signals are out of phase, as in the bottom trace, you can see that the zero crossings are the same, and the peaks occur at the same at the same at the same points, but the traces are going in opposite directions, and the peaks are at opposite amplitudes. And so signals that are out of phase tend to cancel out. So for instance, in multipath propagation, you have two paths for signals coming to your receiver, because one might be direct and the other might be bouncing off a building, and those path lengths are changing. So the relative phase angles of the two signals are changing, and when they're 180 degrees out of phase, you tend to get nulls in the signal, which you can hear as picket fencing, or sometimes, for instance, if you're listening to an FM radio station, you're on the fringe, you're stopped at a stoplight, you notice that if you pull forward very slowly, this signal might get weaker or stronger. And this occurs when you're around buildings in a city or suburb, not so much out in the countryside. The third, the third phase we want to talk about is quadrature, where two signals are 90 degrees out of phase, which is to say, one of them would be, say, the cosine uh, of 2 pi ft, and the other one would be the cosine of 2 pi plus 90 degrees, that quantity times ft. Now, it turns out that sine wave, I'm sorry, the cosine function shifted by 90 degrees is the sine function. And this is important. And this is another sort of trigonometry math trick that gets used because when you deal with quadrature mixers, also called IQ mixers, you multiply. I'm not sure I said before, mixers are multipliers. And so mixers and modulators multiply uh, um, a modulated signal or a desired signal by a carrier frequency, a local oscillator frequency, excuse me. So IQ mixers or quadrature mixers multiply the incoming signal by both uh, the sine and cosine of the carrier frequency. So they're 90 degrees out of phase. Each path contains both sidebands and both the desired and image mixing products. But it also preserves all of the phase. They also, between them, the outputs preserve all of the phase information. So you can, I'm not going to go through the equations here, but if you do the math, you can get it so that you can manipulate those two signals so that you can cancel you can cancel the unwanted sideband or you can cancel the image frequencies from a mixer so that one sideband or frequency range will reinforce and the other one cancels out. This is the basis of the phasing method of uh, um, the phasing method of single sideband generation or demodulation. And it's very common, for instance, in your cell phone, where the local oscillator is actually a digital signal and the mixer is actually a set of analog switches. But that's good enough that you can convert an RF signal down to an intermediate frequency. Now, by convention, the cosine carrier is the I phase, and the sine carrier, which is 90 degrees later, is the Q phase or quadrature phase. So this should, I think, catch us up. Whoop, almost. I want to talk a little bit about digital filters and digital signal processing. Analog filters work in the frequency domain on continuous signals. Digital filters, on the other hand, work in the time domain on data samples. So what you'll see is in a radio that uses digital signal processing, you'll see an analog to digital converter that takes samples at regular intervals. Now, theoretically, digital signal processing can duplicate any analog radio circuit, filters, mixers, amplifiers, and some that uh, you can't easily do in analog circuits. Now, in practice, the highest frequency for digital signal processing is limited by the performance of the data converters, analog to digital and digital to analog. But the performance of digital filters can be better than analog because essentially um, you have perfectly repeatable stages in the digital filter that don't have losses or slight differences in values that regular hardware components do. Now, so what you'll see in radios that use DSP is there'll be an analog front end and then perhaps an analog mixer, but there'll be an analog to digital converter, and all the at least lowest intermediate frequency processing and demodulation and so forth is done digitally, and then converted back to analog to drive the audio output that you listen to with your speaker or headphones. And in the other direction, analog audio from the microphone um, is sorry is converted to digital samples, and then modulation and frequency conversion and filtering, all that stuff is done digitally and then converted back to audio at radio frequency, converted back to analog signals at radio frequencies, and usually pass through a linear amplifier to get the right amount of RF output power. So DSP can be implemented in software, such as in your cell phone, uh, or hardware, dedicated components, or both. Most most amateur most amateur radios that use digital signal processing use software aside from the conversion between digital and analog signals. Oh, okay. Now noise, I want to talk about noise too. Signal is a set of radio waves carrying information. For instance, a radio broadcast. You want to hear the news or listen to music, that's desired information. Interference is a deliberately sent signal that degrades a desired signal. It can be intentional, it can be unintentional. Noise is everything else that a radio receives. Now, there are many sources of noise, and John went through some of them last week. Uh, it turns out that your home electronics create radio noise, and that's why you see an FCC notice on the back of each one, because they have to meet regulations for the maximum amount of interference they can generate. Same thing for the electronics in your car. It also turns out that some noise is natural. If you listen to 80 or 40 meters at night in the summertime, you'll hear static crashes, and those are from lightning strikes. They can be up to hundreds of miles away. You could have perfectly clear weather all around you, but you'll be hearing the radio frequencies generated by lightning discharges. Um, it turns out also um, that stars emit radio waves, and so there's what's called galactic background noise, which isn't noticeable on high frequencies, but as you get into VHF and UHF, it limits the sensitivity of your radio equipment. The thing also to know about RF noise, especially random noise, is that the wider bandwidth signal that you're receiving, the more noise you receive. It's not a one-to-one relationship, but um, but it does again limit how sensitive your receiver can be. So, well, signal to noise ratio is usually the signal power divided by the noise power. And it's usually expressed as a power ratio in decibels, which is logarithmic. Um, so 10 decibels is a power ratio of 10, 20 decibels is a power ratio of 100, 30 decibels is a power ratio of 1,000. And we're going to talk about this in much more detail next week. But the thing to understand is that radio signals and your hearing uh, work on a wide range uh, of, uh, of radio frequency and audio levels. So the typical signal to noise ratios you run into um, are if you want to understand single sideband in a fairly noisy environment, the signal to noise typically has to be 10 dB or greater, which means that the signal has to be 10 times as strong as the noise. And some people with training can make out signals with a lower signal to noise. Some people, especially who aren't familiar with, who haven't had a lot of experience listening to SSB on high frequency, need a better signal to noise ratio. A normal conversation in a quiet room or in an office that doesn't have a lot of noise is typically 20 to 30 dB. And and so if uh, if the signal to noise, if the background noise, for instance, in your family room or in your bedroom is 30 dB below your voice level, then you can understand another person perfectly well, and in fact, you can speak more quietly. Now, theoretically, the digital audio coming from a compact disc has a signal to noise ratio of 96 decibels, which is to say the noise from digitization is 96 dB below, uh, 96 dB below the peak signal levels. Now, that is so good that you basically can't hear it. Uh, in practice, it's not quite that good uh, because uh, music and voice on a CD can be much quieter than the maximum amplitude, but it's still very quiet compared to, say, talking on the telephone or talking where there are noise sources present. However, you have to understand that not true for radios, but the human ear performs worse performs worse in these higher signal to noise ratios when there's more noise present. So if somebody starts a lawnmower outside, you might have to raise your voice to be understood, but the person listening to you will need you to raise it more than just by the amount of noise that's been added. And I think I'm going to finish up here with noise floor. Yeah. The noise floor of a receiver is the amount of noise that's generated inside the radio. So it's the amount of noise in the audio output with no antenna connected. This is because every electronic circuit generates noise from the random motions of electrons. Um, the noise floor is usually expressed in the equivalent measurement of um, of a signal applied at the antenna connector of your radio that produces the same output. And this determines the sensitivity of your receiver. Um, and that's usually done by measuring the minimum detectable RF signal. In other words, when the signal level is equal to the noise level. A noise figure is another way to express it. A noise figure is another way to express that. It's a measure of how much a receiver degrades um, the signal to noise ratio uh, of a particular signal that you're receiving. Now, this is important for very weak signals or near the minimum that your receiver can hear. On the HF bands, is the noise floor is usually of the receiver electronics is usually well below the noise levels that you get just by hooking up your antenna. All this random noise in the atmosphere I've been talking about and from man-made sources too. On VHF, having a quiet receiver or a low noise figure is much more important uh, because the noise you receive over the air tends to go down with frequency. So I forgotten who asked about this last week, but That's the difference between signal and noise floor. Signal to noise is how much stronger your desired signal is than the noise it receives. And the noise floor is the unavoidable amount of noise that you're going to receive, that you're going to hear in a receiver. So that's the end of that. And uh, bear with me for just a second. Boy, I'm sorry. I don't know why my camera keeps cutting out. Now let me go to the end of chapter 5 here, and we'll pick up where we left off last week. Um, okay, let's see what we got here. Here we go. So let's see if I can get this one working. I'm going to talk, this section isn't very long, but I'm going to talk about some aspects of installing equipment um, related to power and noise and safety. We're going to talk a lot more about safety near the end of the course, but we will get there. All right, so let's see if I can get the slide show going here. Okay, yeah, I have the wrong one. There we go. Sorry, I have to scroll way down here. All right, let me do this again. Okay, that was my mistake. All right, can everybody see a slide that says HF station installation? Yes,
Yes.
no, yes.
Yes.
Okay. Well, I'm going to talk about just a few aspects of installing your HF station. Um, and as I say, the safety is going to be the topic of one of the last weeks. So what you need to do is watch out for the consequences of longer wavelengths, higher power, both the amount of power that your radio needs and the higher levels of radio frequency power. So that makes grounding and interference control much more important. And the general class exam focuses on these aspects that are different from VHF. So for if you have a VHF FM transceiver in your car, you have a mobile transceiver, it likely has an output of 10 or 20 watts, which means it probably draws about twice that from your car's electrical system. And that's not a major drain. That's not a major drain, but if you have a 100-watt radio, it when you're transmitting, it draws a peak power of it draws a peak current of 20 amperes or more. Now that is more than you can. Uh, that's more than you can typically get. Uh, that's more than you typically get with a cigarette lighter or auxiliary socket. You know, that thing in your dash that used to be the cigarette lighter. So what you need to do is make sure you have a good low a good solid connection with large wire sizes directly to the battery, these heavy gauges. And for safety's sake, you put fuses in both wires, both the positive and the ground wire. Um, excuse me. There are a couple of reasons for this. One is that the wiring in your car that goes to the cigarette lighter may be thin enough that there's a significant voltage drop, and a significant voltage drop just from the resistance of those wires. And you don't want that. If the voltage at your transceiver goes below about 10 volts or so, it's going to do unpredictable things. Is everybody still seeing the slideshow?
We just lost it.
Bear with me just a moment here.
Yeah, it went away.
Okay, let's see if I can get it back here. I'm having difficulty with my second screen here. So let's see if I can get it. All right, so you should see maybe a blank screen now.
Not yet.
Okay. All right, here we go. Let's do this, and let's see if I can get back to sharing. I'm sorry about this.
All right, now it looks like something's coming. You've started
Okay.
share. Yep.
Yeah.
ACHFS
Now
has
I have to get
started.
the now I have to get the
Oh, now we see the climbers on a rock,
okay.
on a rock face.
Yeah, that's good. Bear with me, and I'm going to
Why would anyone want to do that?
start the slideshow again. And with any luck, this will now you should be seeing the slide again.
Mobile installations, power connections.
Yeah, there we go. Okay, so I'll repeat what I said before. Um, I'll repeat what I said before that you want you want heavy gauge wire to both the positive and negative terminals of the battery. That is the best place to tap off for an HF rig. It's not strictly necessary with a low power rig, but most HF rigs, even those designed for mobile operations, will output 100 watts and draw more than 200 watts at transmit power peaks. Now, this little thing at the bottom says, you know, if you have an older vehicle from the 1980s, which I doubt many of us have, uh, you may have a cigarette lighter circuit uh, that that will give you enough current um, to run your HF transceiver. But I would say don't count on it. Um, don't count on it. And the amount of power that's been available at that cigarette lighter uh, connector has been going down since people stopped using cigarette lighters. Um, I will say also that most car electrical systems are designed for two things, and that is one, to supply a huge amount of current when you're cranking the engine, 100 amperes or more, for a few seconds, and then while you're driving the car, supply enough power to both recharge the battery up to its full charge and operate all the electronics in the car, plus any motors, for instance, such as in your air conditioning. Um, you know, if that's not run off the engine itself, by adding a radio, most cars have generator capacity for things like premium audio systems. So if you're adding a 100 watt, if you're adding a 100 watt transceiver, um, and you only transmit part of the time, you're probably okay. You're probably not going to run down the battery, but you have to be very careful. You have to be very careful about two things. One is that you don't run into problems with the battery running down. And the other is that when you turn off the radio and the ignition is off, the radio is not drawing any current at all. Um, the, with the ignition off, the electronics in your car draw very low amounts of current. Less than 1 milliampere is typical for the whole car. The reason for that is, the reason for that is typically you should be able to start your car again after it's been sitting for a month. Or for instance, you go off on vacation for a few weeks and leave your car at the airport. You want to make sure that that can start when you get back and you're tired and you just want to go home. So 1 or 2 milliamps may not sound like very much, but it is, but over a large amount of time, it can deplete the charge on your battery. So that's another thing that you have to watch out for that's not on the test, but is very practical to consider. Um, as a matter of fact, any accessory you add to your car, when the ignition is off, you have to have a way to make it draw either no current at all or extremely tiny amounts of current. Okay, so there's a little warning if you screw up, if you hook up the power wrong, uh, the smoke will come out of your radio, which is not good. Antenna connections. Uh, typically, antennas on mobile rigs for high frequency bands are electrically short, which is to say much smaller in terms of wavelength than VHF and UHF antennas. Um, for instance, a vertical antenna that operates against ground for 40 meters is going to be 1/4 wavelength long, or 10 meters. That's 33 feet. Well, you're not going to stick a 33-foot pole on your car. It's going to be much smaller. You're not going to stick a 15-foot pole on your car for 20 meters. And what typically happens is you'll get something that's maybe 6 feet tall, maybe a couple of feet taller than your car, and it will have a loading coil in the middle somewhere. Uh, and what that does is makes the antenna look longer electrically. But so you're going to be stuck with a compromised antenna. It's less efficient than full-sized antennas. There's nothing really you can do about that except to choose the one that, that is appropriate for your car. Um, that's the most efficient one that you can find. You can make sure that the ground connections to your vehicle are solid everywhere that you can connect to ground. And um, and the grounding between different parts of a car, uh, particularly unibody construction, may not be all that good these days, which is another thing. And I'm not going to get into the weeds on mobile installation, but it's something to watch out for. But you also want to mount the antenna where it's not right next to a vertical metal surface. For instance, on the bumper of your car is not necessarily very good compared to mounting on the trunk lid. So those are things to watch out for. Uh, Sources of interference for mobile rigs are different from home stations. Um, you can get ignition noise from spark plugs firing, although these days that's not too much, that's not a problem on most cars. You can hear the alternator whine. An alternator is a generator that has rectifiers, nonlinear components that convert AC to DC. And those those rectifier diodes uh, can create radio frequency energy. And even though it's not much, even though it's very small compared to the power output uh, at direct current, zero frequency, if you will, it can be enough that your radio will pick it up. Um, the vehicle's accessories, the onboard controllers, electric motors in fuel pumps, windows, and so forth are all potential sources. Now cars just like home electronics have to be FCC certified so that the electronics on board don't generate, uh, looking at the car as a whole, don't generate more um, RF output than allowed by regulation, but that can still be enough that you'll hear it. Um, Also, things like winch motors, if you have Jeeps or 4x4s, uh, things like that. So you have to watch out for that. And again, there are cures for a lot of these things, and it's sort of beyond the scope of the course. So I'm going to stop and not really say much more. Grounding and bonding. Uh, there are a couple of reasons you want to do this, and we will go into this again in the safety chapter. AC grounding prevents hazardous voltages from appearing on equipment chassis, and even 12 volts can be dangerous if there's enough current behind it. Um, and also to keep RF from circulating where it doesn't belong. Um, Bonding means to connect two pieces of equipment together to minimize the voltage difference between them. What that means is, sorry, uh, because if you have radio frequency energy circulating around where it shouldn't be, in other words, not places other than the antenna and antenna cable, then that can cause problems. That can cause problems with distortion in the transmitter or erratic operation of computer interfaces. You may activate your transmitter improperly. You may not be able to. So this is the typical thing you do. You want to ground the chassis together with heavy heavy wire or braid to a very low impedance bus or hunk of copper, and then from this bus you want to ground the whole thing to earth ground or to the ground at your power panel where the electric service comes into the house. Um, Now, okay, so what you need to do is connect all your metal enclosures together, directly together, uh, RF doesn't RF doesn't circulate uh, over uh, connecting cables. Um, Connecting cables or get induced somehow into the enclosures and into the internals of your equipment. You want to keep connections short, as short as possible and direct, and you want to keep them uh, very big and wide. So you use heavy conductors, 12 or 14 wire gauge, it says here, but you can go to an even lower number gauge, or you can use copper strap that's an inch wide perhaps and a quarter-inch thick. If a lot of if you have a lot of problems with RF in the shack, sometimes what you can do is put a piece of copper flashing or a copper plate underneath your equipment so that so that it gives it a little bit more shielding and other paths for the RF to drain away. Um, and you also have to watch out if if the ground connection is resonant, if the ground connection to earth ground or to the common point ground is an odd number of quarter wavelengths of the frequency you're operating on, it will it won't act as a conductor. It will act to block the flow of RF current. So that way you can get high voltages on your enclosures. It's another reason to keep things short. Now, on high frequencies, a quarter wavelength for most bands is still quite a number of feet, but it's something to watch out for. And you may have to change the length of the ground connection if you run into problems on certain bands. Other things you can do, uh, things you need to watch out for are ground loops, which is to say you have a continuous, you have a connection through two or more paths in a loop. So you can pick up voltages from magnetic fields that exist around your equipment, from transformers and power supplies, for instance, from the AC wiring in your walls and so forth. And that can get into your audio, and it can also get into control signals. It can impose a voltage that's not supposed to be there on your control signals or data signals. Um, oh, yeah, okay. There's a whole table of things. I'm not going to go through this right now, but there's a whole table of things. There are books dedicated to tracking down and fixing grounding problems, radio frequency interference problems, and so forth. So some symptoms are you hear on and off buzzes, humming, clicks, or thumps from things that aren't radios when you're transmitting, or when the interference is source is transmitting. Um, for AM, for AM, uh, for AM, if you're overloading some other piece of equipment, um, for instance, a cordless phone or a broadcast radio, uh, sometimes you'll hear sometimes you'll hear the speaker's voice, which is likely be you. For a single sideband, you'll hear a muffled or distorted sort of duck talk voice um, because there's no carrier there, but you will hear something that follows the patterns of voice, even if you can't understand it. How do you suppress radio frequency interference? Filters are one way. You can place an impedance in the path of of uh, in the path that's conducting the interfering signal. Um, that Now by impedance I mean resistance at radio frequencies, and next week I'll explain impedance in much more detail. But the idea is um, the idea is that uh, electrical signals will take the path of least resistance, quite literally. And so if you put something in the path that will dissipate power at radio frequencies, the amount of current on that path is going to go way down. So, for instance, if you have RF, if you have RFI, if you have RF in the shack, which is normally caused by by grounding or by imbalance in your antenna, for instance, you could if you're grounding and RF suppression isn't good enough, you can get signals on control cables. So if your computer is controlling your radio, for instance, by USB, the USB connection can be broken. And uh, that's very common, especially on the newest transceivers, which have a direct USB connection between the radio and the computer. And the solution for that I've found that a lot of people use is a printer cable that has ferrite beads on both ends of the cable. And that's very effective in stopping any problems with computer control. So let's see. So ferrite beads placed on cables uh, is the thing I was just talking about. Sometimes you can put small, at audio frequencies, sometimes you can put small bypass capacitors from the signal to ground where the impedance at radio frequencies from the capacitor is low, but for at audio frequencies is very high. So at audio frequencies, it looks more or less like an open circuit, but at radio frequencies, it looks like a short circuit to ground, so that the undesired radio frequency energy is conducted right to ground and doesn't get or it doesn't belong in your equipment. Okay, so we're going to do a few questions and then take a break. So which of the following might be useful in reducing RF interference to audio frequency devices? Um, oh boy, I'm not sure I can see the chat window, so if somebody can speak up, what do you say? Yeses, anybody?
Chris is guessing B.
Okay, B, bypass capacitor, and that's correct. Which of the following could be a cause of interference covering a wide range of frequencies? Not using a balun or line isolator, lack of rectification, arcing at a poor electrical connection, or using a balun to feed an unbalanced antenna. Yeses? Anyone?
That'd be C.
Ah, there we go. That is, in fact, an excellent guess. That's the answer. Arcing at a poor electrical connection. Most common places you're going to find arcing is on power lines. For instance, a poor connection at a transformer. And if you can tell the power company where that's happening, they would love to come and fix it, because that means that that's electricity being wasted that they're not being paid for. The other common source is motors. I can hear my clothes washer when it's running. I can hear it on 20 meters to the point where 20 meters is unusable. And RF being generated by motor contacts that are arcing is being fed out into the power lines in the wall. Well, that's Charlie. What sound is heard from an audio device, like a broadcast radio, for instance, here experiencing RF interference from an SSB transmission? A steady hum, on and off humming or clicking, distorted speech, or clear speech? Guesses, anyone? Speak up. Keith, if you're saying something, your audio is muted.
Oh no, I was just saying this one. I don't. I was going to guess C, but I'm not. I don't know.
That's a very good guess.
Oh, okay.
C, distorted speech. What's happening is when you're interfering with a broadcast radio or with a cordless phone, or excuse me, with some kitchen appliance, and that happens. Uh, the That device is acting as an AM detector, and when you listen to single sideband on a radio in AM mode, you're going to hear muffled speech because there's no carrier for the voice frequencies for the voice sideband to beat against. Okay, what happens if you have RFI from the CW transmitter? Humming or clicking, CW, a pure signal, chirpy signal, or severely distorted audio. Keith, anyone? Unmute. Tell me your guesses.
My guess would be A.
Again, a very good guess. You're going to hear on and off humming or clicking when the carrier goes on and off, when you have the key down and key up. Possible cause of high voltages that produce RF burns. Use flat braid rather than round wire for ground wire. Insulated wire has been used for the ground wire. Ground rod is resonant. The ground wire has high impedance on that frequency. Answers, anyone? Keith?
I'll try again. C, I believe.
Let's see if I can see the chat here. Oh, I can see the chat. I think Christopher is guessing C, but the
That was
answer is unfortunately, whoop, sorry. Let's see if I can get this chat down here. Yes, I can. Okay. All right. So the answer is unfortunately D.
D. Oh, okay.
Yeah. Remember I said resonant? Resonant is the same as having a high impedance or being an open circuit at a particular frequency. Again, we're going to get into this in much more detail next week. And part of the problem here you may be having is that we're doing this out of chapter order, for which I apologize. What's the possible effect of a resonant ground connection? Overheating ground straps, corroding the ground rod, high RF voltages on the enclosures of station equipment, or a ground loop. Anyone? And I can see the chat now.
C.
Okay, I hear C, and the answer is C. Yes, high RF voltages. Same answer as the question in the last one. Which of the following would reduce RF interference caused by common mode current on an audio cable? In other words, RF getting onto the shield of the cable. Place a ferrite choke on the cable, connect the center conductor to the shield of all cables to short circuit the RFI signal, ground the center conductor, add an additional insulating jacket to the cable. Anyone?
Uh, A.
Ferrite, put a ferrite bead on each end.
There you go. Yes, the answer is A. I see three of you at least got this one. How can the effects of ground loops be minimized? A, connect all the ground conductors in series. B, connect the AC neutral conductor to the ground wire. C, avoid using lock washers and star washers when making ground connections. Or D, bond equipment enclosures together.
D.
Sorry, C
D is
sharp
in
or
dog.
D dog?
Yep.
D dog. Another way to look at bonding is that you want a very firm ground connection that covers a fair amount of area. And that's important. Area of the ground connection means that the resistance through that interface between the chassis and the ground wire or cable is going to be lower. And so it will be an easier path for RF to drain away or or unwanted voltage difference. Um, okay, what are the symptoms caused by a ground loop in your station's audio connections? You receive reports of hum. The SWR reading for one or more antennas is very high. Station equipment starts to draw excessive amounts of current, or you receive reports of harmonic interference.
A.
Yep, picking up 60 cycle hum from the house wiring would be A. Okay, what techniques helps to minimize RF hotspots in an amateur station? A, building everything in a middle enclosure. B, using surge suppressors. C, bonding all equipment together. Or D, placing low pass filters on all feed lines. It should be easy.
I'm going to
Pardon?
guess C.
I hear a C. I think I see an A from Christopher.
I'd say C, bonding all equipment together.
Yes, it's C, bonding all the equipment together. Um, okay. Why must all metal enclosures of station equipment be grounded? And this is not quite the same answer as we've been getting the last few questions, or not quite the same reason.
I
Christopher
agree with
says,
Chris. I
Christopher says,
agree, D.
yeah, okay, yes, it's
P
D.
delta.
Yep. Hazardous voltages don't appear on the enclosure, which is what you normally touch. Okay. Uh, Now going back to the beginning of this section, which of the following direct fuse power connections would be best for a 100-watt HF mobile installation? A, to the battery using heavy gauge wire, B, to the alternator or generator using heavy gauge wire, C, to the battery using insulated heavy duty balanced transmission line, or D, to the alternator or generator using heavy duty balanced transmission line.
A and both should be fused. I took a class and you have to twist the wires when you take it to the battery to
Really?
reduce. Yeah, I took a class on how to hook it up. And they recommend that you twist both the wires together when you run them to the battery.
Okay.
The reason it on the RF, it dissipates all the RF signals on the wires.
Yeah,
If you
yeah.
don't twist them, if you don't twist them together, it creates noise. That's what they told
Well,
me.
it allows noise to pass more easily. It doesn't reject noise as much. Yeah, twisted pair Ethernet works that way, as Chris is saying. That the twisting, well, and also being a balanced pair um, with equal and opposite signals on the two wires, those prevent picking up those prevent picking up uh, induced voltages. Okay, why should DC power not be supplied by the vehicle's auxiliary power socket or the cigarette lighter connector? A, not wired with RF shielded cable. B, the wiring may be inadequate for the current drawn by the transceiver. C, the polarity of the socket is reversed from the polarity of modern HF transceivers. D, drawing more than 50 watts could cause the engine to overheat.
B.
He is in.
Bravo.
Yeah, absolutely is B. All right. Um, let's see here. All right, at this point, I am going to stop sharing if I can here. I'm missing something here. There we go. Yes, no. And we are running late, so let's take a 10-minute break till 25 minutes past. Oh, here we go. Here's my stop share. And I'll turn on my video. We can take a 10-minute break here and we'll pick up again right at 25 past the hour. Um, what I would like to do now, yes, what I'd like to do now is to go through um, digital modes. And yeah, you're right. Chris is saying you want to see log, sine, and cosine. You don't actually need sine and cosine for the general class test. But yeah, that's typical of a scientific calculator. And if you look in the chat, he has got a link to somewhere for a $15 calculator.
Must be Amazon.
Okay.
I'm guessing. I don't know.
But seriously, I don't know how often people typically go to the dollar store, but it's really worth doing. All right, so I'm going to share the screen again, and we're going to do digital modes, which is a completely different topic here. And I will try and get through everything, but we'll see. Okay, so um, you should probably see my gray screen background here, and let me
Yep.
start
The
the
guy climbing the,
slideshow.
yeah, we see it.
Guy in a red jacket on the face cliff.
Yeah, I've kept that through, I think, 3 different computers now.
It's your Rock of Gibraltar.
Is it? No, I think it's probably somewhere out in the Western US.
That was a joke, sir.
Anyway, okay. So let's see what we can do here. Uh, this is chapter 6, digital modes. Most of this is the ARRL slide set, but I have added some things. And I'm going to do some very basic stuff right at the beginning here. I'm going to get the chat back. Oh, okay, there we go. So let's do the basics here. A digital mode is text, data, voice, images transmitted as bits over the radio. Some digital modes are commercial and some are used only by radio hams. I'm sorry, some modes that you'll see on the ham bands are commercial and some are only used by radio amateurs. Some modes are historic, some of them are very new, like within the past 5 to 10 years. Uh, the FCC regulates digital modes based on type, data rate, and bandwidth, although the regulations are changing. So, amateur digital modes, there are many of them. And I won't lie, uh, there are a lot of acronyms and they're all alphabet soup. So, for this chapter, you're going to have to do a lot of memorizing, unfortunately. And what you'll hear when people talk about these is they'll use the acronyms. And so if it sounds like people are just zipping things by you when you hear them talk about different digital modes, then uh, there is a lot of jargon, and it's not necessarily anything that makes sense in plain English. So most popular digital modes, by far, the most popular digital mode is FT8, which is less than 10 years old. And there's one called FT4. These were very popular about 5 years ago at the bottom of the sunspot cycle when HF propagation was lousy because they are weak signal modes and they will get through when other modes can't. Radio teletype is probably the second most popular. It's PSK31 and a faster version called PSK63, which are essentially chat modes. Um, where you type things at the keyboard and PSK31 runs at about keyboard speed. You can type maybe a little bit ahead of it, but only if you're a very good typist. There are packet radio modes that operate very much like TCP/IP on the uh, internet. There is something called Whisper for weak signal something or other reporter. And the idea is to see who can hear your very weak signals. There are monitoring stations all around the world. There's slow scan television where you transmit images at low resolution in anywhere from 10 seconds to, I want to say, about a minute and a half, depending on whether it's black and white or color, depending on the resolution. Um, and there are digital voice modes. Uh, you're probably familiar with D-Star DMR System Fusion from VHF FM. There's also one called FreeDV, which is used on the HF bands primarily because it has very low bandwidth. Now, this lesson in the book are mostly about text modes, which they call data modes. Um, and digital text modes must use the CW, CW and data band segments, the ones that are reserved for CW and data. Uh, Digital voice modes and slow scan TV must use the band segments where voice is permitted. Because digital voice is treated as voice and slow scan TV, although it's primarily driven by software and is more or less digital. Uh, it's historically television is an analog signal and that carries images and voice, and so it's it, so slow scan TV is used in voice band segments. Now you'll hear some people say CW, Morse code, is digital because it's on and off, and opinions vary. Um, because CW doesn't transmit bits, it transmits dits and das and pauses, which have different lengths. Uh, and it's the combination of those things that have meaning. So it's not a simple binary code. So if somebody says CW is digital, you can look at them skeptically, or you might think, well, if you squint at it right, yeah, it's digital as opposed to voice. So what makes something a digital mode is a combination of a digital protocol, which is how the bits are handled, and a modulation method, which is how the digital bits are impressed on a radio frequency carrier. So the names of some of these things, names of some of these modes could refer to either one. So it's important to understand. It's important to understand, just like I don't know how many of you are all probably old enough to remember dial-up modems from 25 years ago. And what you connected to your computer was a cable uh, that connected to a serial port that was sending bits. What went over the telephone line was audio, uh, and it was audio. It could be, in fact, rather complicated to squeeze the maximum bit rate out of limited bandwidth of the telephone line. But it was a modulation method, is what you heard on the telephone. So similarly, what you're going to deal with generating and decoding digital data or digital text signals. It's all digital, but the modulation converts digital to analog and vice versa. So there are a lot of digital modes because they are optimized for different things. You can optimize for speed, reliability, uh, narrow bandwidth, error-free transmission, um, success in difficult conditions such as noisy or fading environments. But you can only get a couple of these. You can only optimize for one or two of these things out of the five. And there are always trade-offs to be made. So what you'll find is different protocols, different modes, excuse me, will work well under different circumstances and for different purposes. And to give you some idea, in 1980, people used teletype machines. That, in fact, is not, that, in fact, is more modern than the picture on the left is more modern than some of the teletypes, which were cast-offs that people used in the 1960s through 80s or so, where there would be something that translated two voltages into two audio tones for the radio to transmit, or vice versa, transmitted two received audio tones into an on or off signal. On the right is FL Digi software, and it may be a little bit difficult to make out, but at the top, at the top one quarter or so is read control. Uh, the uh, the second quarter there is what's actually being transmitted and received on the air. And the bottom is a display of the spectrum. And you'll see, maybe you can see right here, these two, these two red things right below the scale. And there are two sort of vertical lines below it. That is a tuning indicator. And you want to get those two red marks on the right on the two frequencies that are being transmitted. So typical station setup is a computer, a radio, and an antenna, and then something that converts digital signals from the computer to audio, uh, going to and coming from the transceiver. And then there's push to talk control so that you can switch between transmit and receive. Now, the radio I have, which is I want to say the design is about 5 years old. Just has a USB cable that connects right to the back of the radio because this this audio interface is built into the radio. You'll find that sometimes people use the headphone and microphone connectors on their computers directly, but most people use some sort of external sound card or audio interface box. And you can theoretically use just about any radio capable of transmitting single sideband with one of these and work digital modes. So this is what a piece of digital mode software looks like in a little bit more detail. And again, this is FL Digi, which is pretty ubiquitous. And you can see the top uh, small section here is the top small section here is rig control, what frequency you're on, who you're talking to, where the signal reports you exchange, and so forth. And this part will talk to your logging program. This in the sort of tan section here is and sort of tan section here is the the QSO, the conversation that's in progress. Over on the left here, there's a panel that will decode uh, signals in the um, all the signals in the audio bandwidth of the receiver. So you can see, if you look at these things, they're fractions of a kilohertz apart. And that's because it's decoding several signals at once. And if you look on the bottom there, you will see on the spectrum display that left to right, there are several signals on different frequencies that are within the audio bandwidth. Oh, what looks like gibberish in the tan panel is the decoding is not always perfect. And sometimes if nobody is transmitting on the frequency you're listening to, the decoder will decode noise into gibberish. So that's noise. And that is a problem with some of these modes. But it's something where you can generally recognize what's supposed to be happening and what's not. So to give you some idea of how many modes there are, I just took the mode selectors from the two most popular digital mode programs, and there they are. There's a huge list that we are not going to go through everything. On the left are typical digital modes that have evolved over a long period, and on the right are weak signal modes, which are generally a lot more recent. And you'll notice that the first selection here is CW. It turns out FLDigi can send and receive CW. It can decode CW. It can convert text into Morse code characters that it transmits. And some people use that for contesting so that they're not constantly pounding on the key. So now we're going to get into most of the ARRL slides. So this is looking at this from an operating point. Communications are digital modes. If information is exchanged as individual characters as encoded as digital bits. Well, so Morse code, I said maybe radio teletype, PSK31, etc. So these first, so through FT8 are digital text, but you notice that to the right, D star DMR, digital voice, slow scan TV is digitized images. Um, this statement on the slide is a little bit misleading, and what we're going to talk about here is mostly digital data modes or digital text modes. So digital text modes are restricted to the CW data only segments of each HF band, which is generally near the bottom. Uh, by gentleman's agreement, and you'll see in the chart in your manual, pardon me, uh, the digital modes are usually on frequencies near the high end of the CW segment, um, and they generally don't interfere with each other. People are generally pretty considerate of others here, so that, for instance, you don't hear a PSK or an RTTY signal, radio teletype signal, in where FT8 is normally used on those frequencies. So data rates and bandwidths are specified by the FCC rules. Um, the FCC, the rules and regulations talk about some specific modes, in particular radio teletype, but radio hams can use any digital mode as long as the details are published. In other words, if somebody describes the protocol and the modulation method somewhere in literature that's publicly available, then you can use that mode. And radio teletype, for instance, originally used mechanical teleprinters, like in the picture I showed several slides back, but now it's all done in software. PSK31 is a good weak signal mode. It works for fairly weak signals, and it uses fairly narrow bandwidth so that you can chat in band using less radio bandwidth than radio teletype. Radio teletype is a legacy mode. Amateurs started using it in the 1960s. PSK31, I think, comes from the 1990s, and maybe somebody can correct me, but anyway, there are packet modes. PACTOR and WinMore are discussed in the uh, and have exam questions, although they aren't really used very much these days, except for emergency communications and, interestingly, for communications with sailboats. Packet radio is very common in the VHF and UHF bands because the bandwidth and bit rate limits are high enough that it's easy to use. So I want to talk about bit rates and bandwidth. Most countries, except the United States, only regulate the bandwidth, the amount of radio spectrum that a digital signal can use, and they don't specify how fast the digital mode can transmit. In other words, the data rate. So the FCC, effective only this past January, changed the rules. So on the HF bands, except for 60 meters, digital mode transmission can use any modulation method at any data rate as long as it occupies no more than the same bandwidth as a single sideband signal, 2.8 kilohertz. But the rules are different for the 60-meter band. Those have not changed. Um, the, there are two uh, amateur radio bands below the AM broadcast band on low and medium frequencies that we haven't talked about much, and those are very narrow. So there are very strict limits on data transmissions there. And the VHF and UHF bands, the VHF bands, uh, and I think 440 megahertz have baud rate limits. In other words, data rate limits for digital transmissions. And above and higher bands than that have bandwidth limits. And the FCC is considering changing the rules to all bandwidth limits. So what you're seeing here is sort of an evolution of the regulations and to be more consistent with modern practice. And to give you an idea why, again, going back to dial-up modems, you remember, you may be old enough to remember when a dial-up modem was 300 baud, 300 characters, or 300 bits per second, excuse me, and you put the telephone handset in sort of cup holders on the modem body. And then it was 1200 baud, and then 2400 baud, and then 9600 baud. Well, the bandwidth of the telephone line is only about 3 kilohertz. So the how did these modems get so fast? In fact, some of them went even faster than 9600 baud. And the reason is, the main reason is they used tricks so that they were able to have a higher bit rate in the same bandwidth. And that's something that the FCC used to care about, but now cares about much less. It cares about the width of signals in the radio spectrum and not so much how they get there. So, and we're going to go through some definitions in a couple of slides here. This is one of mine, and we'll catch up. So again, this is a table that you have for what are the common range of frequencies for digital signals on the HF bands. And if you look at the regulations for CW data segments, you'll see that these CW segments are generally wider. For instance, on 80 meters, the CW and data segment goes all the way from 3.500 megahertz to 3.600. But the bottom 70 kilohertz is reserved for CW. Okay, so let's see here. So let's do some definitions here. An air link is the part of the communication system that involves a radio transmission. That's the analog part. A bit is a fundamental unit of data, 0 or 1. You know that a byte is 8 bits. The bit rate is the number of digital bits per second sent from one system to another. A baud rate is the number of symbols per second sent from one system to another. The difference is one baud can represent multiple bits. For instance, the FT8 protocol, uses 8 frequency shift keying. It uses 8 audio frequencies, any one of 8 audio frequencies. So so that when you receive that audio tone, it could represent one of 8 different values, or 3 bits worth. Three binary bits can represent 8 different numbers. So you can send multiple bits per baud depending on the modulation method. The duty cycle is something different. The duty cycle is the ratio of time when the transmitter is on as opposed to the total time on and off. So for instance, CW has a duty cycle. When you're transmitting, CW has a duty cycle of around 50%. AM transmission because of the carrier that's on all the time, or radio teletype because one of two tones is on all the time, have duty cycles of 100%. The protocol, the protocol is the way that the data bits are handled. And we'll get into some of the, in a couple minutes, we'll get into some of the ways that this happens. Uh, the mode is the combination of protocol, as I said, with the modulation method. So we went over modulation methods last week. Uh, Single sideband, phase modulation, and something called frequency shift keying, which I'll show in just a moment. Um, there's phase shift keying. There's something called spread spectrum modulation, which we may not touch on. Um, anyway, uh, as a reminder here, the digital voice modes are regulated as voice emissions, including the digital modes that you see on VHF FM and also single sideband. I'm sorry, slow scan television (SST) is treated as a voice mode. Okay, frequency shift keying. The individual bits are encoded as tones. For radio teletype, you use two tones. One represents a zero, one represents a one. Um, for radio teletype, for radio teletype, the one is called mark, and it's also the idle state of a teletype machine. A space, uh, a zero, excuse me, is called the space. So it's mark and space for one and zero. And there are two different ways. There are two different ways to do this in direct FSK. The VFO, the frequency of the VFO is modulated by a digital data signal. So it hops between two frequencies. And excuse me, for audio frequency shift keying or AFSK, which is much more common these days, audio tones are used to modulate a single sideband or FM transmitter through the mic input, or more commonly these days through the auxiliary audio input. Most fairly modern HF transceivers have an aux audio input on the back panel, which you can use so that you're not plugging and unplugging the microphone. Oops, sorry. Okay, let's go on. And so if you have more than two tones, you have multiple FSK or MFSK, and you can create more codes, more bits per baud, more bits per symbol. Phase shift keying is a little bit different. The most common is to take a carrier and invert the phase to so in other words, send it a 0 degree or 180 degree phase. And there are a couple different ways to do that. And the idea is that it's fairly easy to detect if you have a constant carrier reference in the receiver to measure the phase against. So what you hear is a sort of buzz or a raspy sound that is a little bit like one of those dial-up modems I was talking about. I think I actually uh, played one, and it was a very light buzz when I played in the first week a PSK 31 signal. Well, here we go. We're going to do some practice questions here. What segment of the 20-meter band are most digital mode operations commonly found? At the bottom of the slow scan TV segment near 14.230, at the top of the SSB phone segment near 14.325, in the middle of the CW segment near 14.100, or between 14.070 and 14.100, which is the top of the CW segment. Anybody?
I believe it's
D
D.
delta.
D delta, yeah, that's right. How is direct binary FSK modulation generated? By keying an FM transmitter with a subaudible tone, by changing an oscillator's frequency with a digital control signal, by using a transceiver's computer data interface protocol to change frequencies, or by reconfiguring the CW keying input to act as a tone generator. Chris is saying B, bravo. And the answer is B. By changing the frequency, by directly changing the frequency of an oscillator using a control signal. How are the two separate frequencies of a frequency shift key signal identified? FSK, dot and dash, on and off, high and low, mark and space.
D,
D
delta.
delta.
That's right, mark and space. Which of the following provide digital voice modes? Whisper, MFSK 16, EasyPal, FT8, FT4, FST4, WinLink, Pactor 2, Pactor 3, or DMR, D-Star, and System Fusion.
D
D.
delta.
Yeah, easy one, that's Delta. Okay, character-based modes, which is probably the last we're going to hear about voice for this lesson. The simplest use of digital communications is a mode in which individual characters, in which you sit at a keyboard and you transmit to another station where they're read on a screen. Now, CW is one such mode, but things like radio teletype and PSK31 are the real digital modes we're going to talk about. So the speeds are low, but they're convenient to use and they don't require any particular extra equipment. And you know, your laptop or your desktop computer does the heavy lifting here. It acts as to modulate and demodulate. It acts as a modem for these amateur digital modes. You don't need special hardware. And you'll sometimes hear these modes talked about as keyboard to keyboard or chat modes. So the way these character-based modes work is to transmit a stream of characters without really much structure. It's sort of free form. Either you're on the air and be idle or sending data, or you're listening to somebody else who's doing those things. That means your transmission can have pauses in it in which your transmitter is sending a tone, but there's no information in it. And if you think about the way you type, that would make sense. So let's look at radio teletype here. Radio teletype uses radio teletype uses uses 8 bits or 8 characters that consist of 8 bit times. There's a start bit which always consists of a space that signals the start of a character. At the end are 2 stop bits, which are both mark, which indicate the end of a character, and in between are 5 data bits. Um, in in uh, in sorry, in communication over a dial-up modem, you used ASCII, which was 7 bits, and sometimes there was a parity or a check bit for the 8 bit, plus a start bit and 1 or 2 stop bits. Radio teletype uses something called Baudot code, which dates back, I believe, to at least World War II, and it represents 32 values in 5 bits. And that has some interesting consequences, which I believe we get to pretty soon. But the idea is when you're sending radio teletype, start of a character is always a space and the end of a character is always two stop bits. And that's usually enough information to synchronize the transmitter and receiver so that the receiver doesn't start decoding in the middle of a character. So the FCC has a special name for it, narrowband direct printing telegraphy. Uh, so here's the thing, the Baudot code uses 5 bits for 2 different characters. That means that you can't get the 26 letters of the alphabet and 10 numbers and punctuation. So there are 2 special codes called letters and figures that switch between 2 character sets, which are called the letters and figures character sets. Letters is 30 is 30 codes that represent the 26 letters of the alphabet plus a few special characters. And then the figures are the numbers plus a bunch of special characters, things like dollar signs, for instance, and asterisks. So the idea is when you receive a letters or figures character, then you for the following the trans the characters following that use that particular character set until one of 2 things happens. Either you receive another letters or figures character, or in some cases, when you send a space character, when you send a space character, it will unshift. So space also shows up in both character sets. So we're talking about a shift as in upper and lowercase or uh, between letters and figures, but there's another meaning to shift, and it's important not to confuse the two. And the difference in frequency between mark and space tones is called the shift, as in frequency shift keying. And these days, it used to be decades ago, people used an 850 hertz shift. 850 hertz wide was the width of a radio teletype signal, plus a little bit because the signal was changing. Uh, these days, the most common frequency shift, not phase shift, the most common really frequency shift is 170 hertz, because modern receivers work well with that narrow, with that narrow shift. PSK 31 is the most popular PSK mode. Again, it's character based. It doesn't have structure, and it's somewhat different. You use the sound card to generate PSK signals, and it can generate audio with phase shifts built into it. And 31 is a symbol rating baud. It's actually slightly higher. It's designed for keyboard to keyboard communications. You can type up to about 50 words per minute, and PSK 31 will keep up. So it's also called BPSK 31 for binary PSK 31. So there's also a mode called QPSK 31 for quadrature PSK 31, which sends 2 audio tones. So there are 4 possible phase shift combinations, 0 and 180 degrees on each of 2 audio carriers. And obviously you can go twice as fast. Um, all data modes, all data modes are pretty much sensitive to using the correct sideband. And So it says here sideband sensitive, and uh, getting ahead of myself, every mode except every mode except RTTY, like convention, uses upper sideband. PSK uses a variable length code. You don't use 5 data bits, you use fewer data bits for more common characters and more data bits for uh, longer characters, for less common characters, excuse me. It's much like Morse code. Morse code for E is 1 dit, for T is 1 da, for I is 2 dits, for M is 2 das, and so forth. So that the most common letters have the shortest most Morse code representations, and PSK31 varicode is the same. The most common letters E, T, A, I, O, N, etc., have the shortest binary codes. It takes it so by convention, capital letters and punctuation use longer codes. Radio teletype, since it only has one set of alphabet characters, it's all uppercase. For PSK31, it's common to see people using all lowercase because capital letters take longer to transmit. You can do it. It's not wrong, but by convention, you don't use the caps lock. You don't transmit in all uppercase. PSK31 and QPSK31 have about the same bandwidth, which is just a little bit narrower than a single sideband voice signal. Whoop, yep. QPSK31 has extra bits, so some of its encoding provides error detection. And I think we'll talk a little bit about error detection versus error correction. It is after 9 o'clock, so the question is, what do people want to do at this point? I can continue next week. I can go for about 15 minutes here. What would people like to do? Would you like to stay for 15 minutes, stop now, or what? I can't get through everything in 15 minutes, that's for sure.
I
Let's
could
say
do
we go to 9:30 again, and then I will be super organized next week, which is important because next week is going to take some hard work on your part. Okay, so we'll go till 9:30, and somebody speak up when it's 9:30 because I can't see I can see a clock here. All right. But if I don't slow down and it's already 9:30, stop me, okay? Practice questions. What's the most common frequency shift for RTTY on the amateur HF bands? Anyone?
B.
B Bravo. Okay, yes, it's B Bravo, 170 hertz. Which of the following is characteristic of QPSK31? It's sideband sensitive. Its encoding provides error correction. Its bandwidth is approximately the same as binary PSK31. Or all these choices are correct. Guesses? Unmute, make a guess. All right, in the interest of time, it's D. All of these are correct. You need to be listening on the right sideband. QPSK gives you some, not sure if it's error correction or error detection. But it makes it more sure that what you're seeing when you receive is correct. Its bandwidth is about the same as BPSK31. What describes Baudot code? 7-bit code with start, stop, and parity bits, a code using error detection and correction, a 5-bit code with additional start and stop bits, a code using cell call and listen.
I believe it's C.
C from Chris. I hear a C. So yes, it's C, 5-bit code. Very ancient. Which of the following statements is true about PSK31? Uppercase letters are sent with higher power. Uppercase letters use longer bit sequences and thus slow down transmission. Error correction is used to ensure accurate message reception, or higher power is needed compared to RTTY for similar error rates.
B.
B. Yeah.
B, everybody agrees is B. PSK31 actually works fine at lower power levels than RTTY. And error correction is not there when you're using plain PSK31, one with a single tone carrier. What type of code is used for sending characters in a PSK31 signal? Varicode, Viterbi code, volumetric code, or binary code?
I think it's A.
A.
Yep. I see a couple A's, and the answer is A. Varicode is what it's called. Okay, well, how much time do we have? All right, I'm going to try and go through packet-based modes fairly quickly here. Think internet. When you send an email or you're looking at a web page or stuff like that, data is sent over the internet in packets that have structure. And so packet modes are derived mostly from computer-to-computer network protocols. Hams have adapted internet and computer protocols for packet radio, including Pactor, Winmore, and other communication systems. Some packet modes require precisely defined timing, and there's utility software available. Well, when I talk about FT8, I'll talk about that. But let's talk about things that are considered to be pure packet modes here. So for the basics, the packet refers to a structured group of data that's transmitted in what's called a frame. Frame consists of a header, which contains synchronization, routing, control, status, a data payload in the middle, and a trailer at the end that contains status and error detection data. Now, the header and the trailer are normally fixed length, and the data is commonly, though not always, variable length. It can be anywhere from 1 to some large number of bytes long, similar to TCP/IP. So you folks with IT backgrounds, some of this will be very familiar to you. Whoop. So let's see if I can do this. Okay. Oh, I just went through that. All right. So first thing that you have to do is when a packet transmission starts, the receiver has to synchronize with the transmitter. So there are usually fixed bit patterns within the header that serve to synchronize the receiver to the timing and bit pattern of the transmitter. There are also control and routing information, and in some cases, information helps with error detection and correction. These indicate what to do with a particular packet, particularly if a packet is retransmitted, or if it has a serial number, or if it has more than one destination in the receiving computer. The data is usually ASCII characters, 7 or 8-bit characters, and usually it's compressed, but not always. And then the trailer contains additional information that says, well, this is the end of the packet, and it can contain error detection codes. These slides are a little bit off, and so the IT types don't cringe quite yet. Usually what you'll see in a trailer is if there's error detection, if the protocol supports error detection, you'll see some sort of uh, error detection
Oh,
cyclic cyclic redundancy check or CRC code is very common. And the idea is the characters of the data packet are multiplied and shifted together in a way so that uh, an error of 1 or 2 bits or several bits is easily detected. Forward error correction. Forward error correction is where you use extra bits so that when the data is combined and decoded in the receiver, um, you might use 50% extra bits, 50% more bits than you use to send the raw data. You might use twice as many. And what that does is it will detect, it will allow you to correct errors. If it's 1 bit off, the decoder says, oh, this is really the letter E or the letter Q, but it doesn't get them confused. And depending on how much forward error correction there is, in other words, how much bandwidth you devote, how many extra bits you devote, which is more bandwidth to error correction, um, you can you can you can correct up to several errors in a packet. And the reason for errors is between the transmitter and receiver, you can have fading, you can have noise that's heard at the receiver that will cause errors in the demodulation or cause missing or wrong bits in the demodulation. So this slide is a little off. And going to, oh yeah, okay. So here's the thing. For error detecting systems, uh, you have something called ARQ for automatic repeat and request. If a miss, so what happens is messages ping pong between two stations. And so if you're receiving, if station B receives a transmission from station A, but the uh, the the check code that it calculates on the received data doesn't match the check code that was sent by the transmitting station. It says a no acknowledge or not acknowledge, commonly called a NAC. If everything is fine, if the codes match up, which means the likelihood of an error, that an error is unlikely to have happened, an undetected error is unlikely, it will send an acknowledgement or a positive acknowledgement called an ACK. So you send the, so station B sends an ACK or an ACK back to station A. Uh, and so station A will retransmit the same packet until it receives an ACK or until the number of retries times out. Most systems only have a limited number of retries because otherwise you'd be hogging a radio channel. And so ARQ systems, this mechanism is pretty automatic. And sometimes the ACKs or NACKs with are sent in messages that also contain the data payload so that the acknowledgements and retransmissions can go in both directions. Sometimes the ACK or NACK is sent in a very short data packet. So because most of the time the data is only coming, the desired data is only being transmitted in one direction. So at any rate, ARQ is used in Pactor, packet radio systems, WinMore, and other things. They were designed for um, wired network connections. And what that means is you can get error detection from any number of receiving stations. In other words, if I'm listening to a packet radio conversation between Ralph and Keith, say, and my receiver detects, oh, there's been an error in that last packet that Ralph sent, Keith's station can Keith's station can send a NAC and ask Ralph's station to retransmit that same packet. But I can't because I'm eavesdropping. I'm not part of the conversation. So that means you can't break into an ongoing contact. And that's important. What that means also is um, in a in an ARQ system, automatic repeat and request, generally one pair of stations is using the frequency until they're finished with a conversation, which can be several minutes, depending. So you can't really get on and say, oh, the frequency's busy, or say you're interfering with me. Okay.
So I have a question on that.
Yes, go ahead.
Um, and I think this probably just shows that I'm still not visualizing what's happening yet, but in those, you said you can't break in, but can you hear what they're saying?
Yes, you can eavesdrop.
Okay, you can eavesdrop. So that means that those two stations have to announce their handle every 10 minutes still.
Their
Is
call
that
signs, yes,
correct?
absolutely.
Okay.
Yes. You're just listening to a radio. You don't have to do anything. Just sit there and listen. The rules are the same for amateur radio and broadcast radio. If you're transmitting, yes, you have to follow the FCC rules and send your call sign at least every 10 minutes. So uh, ARQ also provides a broadcast mode so that one station can pop up and say, "I'm here."
Shoot.
Sorry, Bob. Bob, did you say something? No,
No, I didn't.
Sorry.
no, the other Robert, the other guy. But okay. Um, and eavesdropping is also called monitor mode. So in monitor mode or eavesdropping, you can listen to other conversations, but if your station detects errors, if the transmission wasn't error free as you heard it, you can't do anything about it. You have to live with it.
Okay, you are at 9:30 now, though.
Okay, I'm at 9:30. I'm gonna get through a couple more slides and then stop before we get to questions. So let's just go through ARQ a little bit more so we find an easy place to stop. So so as I said before, you can't break into a contact that's in progress. You can't break in for any reason really, even to say, oh, my traffic's more important. Okay, and at this point, all right, one more. So these systems that end in Tor um, are developed to compensate for transmission errors in radio teletype. In other words, it adds error correction to something that's like radio teletype. And packet radio is used almost exclusively on UHF bands. In fact, not on 6 or 2 meters, but higher than that because of the bandwidths that they occupy. And sorry. The Tor systems also do error correction. So they send short bursts with error detection and correction, and they're based on packet switching protocol X25, which is very old, but has been adapted successfully to amateur radio. You can use VHF FM at 1200 or 9600 baud. And I believe on bands 440 megahertz and up, you're restricted only in bandwidth. So more. Doesn't work on HF because the data are easily disrupted by noise and fading. And so we're going to stop here, and I'll talk about protocols designed for the HF bands next week. So we're about halfway through this, and my apologies for once again running over. So next week we are going to finish chapter 6. We will start on chapter 4. We're going to go through the first couple sections of chapter 4 about how you measure uh, um, electrical and radio signals, what impedance means, and the different, getting into different components. No, we're going to do power and decibels, AC power and measurements. So we're not going to get into how the different electronic components work. So for that, I'm going to apologize in advance, but you're going to have to dust off some of your high school math. And this is a hard part for people who aren't techies by nature. I'll warn you in advance. So I will try and be as clear as possible and give you good information. Give you good information, uh, um, and so that you understand this. Because once you get a grasp on these things, a lot of understanding comes very easily. And the key here is that radio, amateur radio and electronics deal with very wide ranges of quantities, which is why we use decibels and logarithms. Okay, so for next week, please read chapter 4, section 1 and 2, and we will finish chapter 6 here at the beginning of time next week, and you're stuck with me again. So before we wind up, are there any questions?
You did a good job.
Okay. And Chris, I will try and post the link to the recordings as soon as they show up, but you can always check on YouTube at, pardon me, at Jerry's W9NPI channel, or in fact, just type in his call sign W9NPI and you'll pick up on it. And usually Bob gets the recordings to Jerry within a day or two, and Jerry puts them up right away. So I appreciate people taking the time, and I appreciate people taking time and sticking with me this long. And once again, we're using a new set of slides and a new question pool, so you'll have to pardon your instructors until we get more familiar with this. And I will be doing more work. I will be doing more work over this week to streamline these presentations more, because it's very obvious they're too long for 2 hours. So, and I'll crack the whip on my other two instructors. So thank you for coming, and I'll say goodnight to everybody. And then let me stop sharing here. Bada boom.